Well, good morning and greetings. I'm Kate Ely, hydrologist for the Confederated Tribes of the Umatilla Indian Reservation. 3 tribes, the Walla Walla, Umatilla, and Cayuse, were brought together by the Treaty of 1855 as a sovereign nation with reservation lands in northeastern Oregon and ceded 6.4 million acres in Oregon and Washington, and with the hunting and fishing rights and usual and custom sites and in parts of the western United States. So my presentation is water, CTUIR, surface water and groundwater for first foods and people. Okay. This is an overview of the topics I'll be highlighting today. There's quite a long list, and this is a relatively short program for this list, but we'll get through it. Okay, and hopefully you'll have a better understanding of surface water, groundwater, and their inseparable connection, and the understanding of the water cycle and the human effects on the water cycle, watershed, and first foods. And then we'll look at climate change and what is anticipated and the impacts to first foods. So lastly, we'll look at what we can do to combat climate change. Okay, so I work in the Water Resources Program, and our goal is to ensure clean and adequate water to produce first foods, and also to ensure water supplies for economic and community development of the reservation. Okay, but we also manage tribal water resources for sustainable use under a changing climate. Okay, so what are the first foods? Let's look at those. They're CTUIR, Nusuk, Yamish, Couch, and Wiwinu. In other words, water, salmon, deer, cows, and huckleberry. And within the Department of Natural Resources, we have a mission statement that was adopted in 2007, and that's to protect, restore, and enhance the first foods, the water, salmon, deer, cows, and huckleberry, for the perpetual cultural, economic, and sovereign benefit of the CTUIR. And we will accomplish this utilizing traditional, ecological, and cultural knowledge and science to inform population and habitat management goals and actions, and natural resource policies and regulatory mechanisms. And the department has developed 2 guiding documents to help us implement this mission. The first document is the Umatilla River Vision, and it's to address the interconnection of the first foods and people's responsibility to protect and enhance those first foods. The 5 touchstones are aquatic biota, which are fish, bugs, and the like, all that living. The riparian vegetation, the plants along the stream corridor. Geomorphology, the landform. Hydrology, which is both the water quality and quantity in stream flows. And the connectivity of the river, the floodplain, and groundwater. And the floodplain is basically river deposited sediments that we would have in this area along the river. As we will see, the water in the rivers is mostly supported by groundwater. In 2019, the department developed the First Foods Upland Vision. And these are this is the second document to assist us in protecting, enhancing the first foods. And common to these two documents is the fundamental touchstones of the interconnection of the first foods, the land and landforms, the hydrology, and the biota. Okay, so now let's look at the world's water and distribution. And this is an image from NASA that shows the eclipse crossing North America. But let's look and we'll see the area on the surface of the Earth is covered by water. And of that water, 97% is ocean water, not drinkable water. And 3% is fresh water. So of the 3% fresh water, most of it is tied up in the ice caps and glaciers to the north and south of us and on the high elevations. 69% And then groundwater supports 30% of that fresh water. And then accessible surface water is really just 1% of all the fresh water. Now let's look at what is available as far as fresh surface water. 52% of it is in lakes, 38% is in soil moisture, and 8% in water vapor, which is the water in the atmosphere and clouds, and 1% of that accessible surface water is in rivers. So basically, water that we see in stream is 1% of accessible fresh water, and 1% of surface water, and of 3% of all water. So there's very little fresh water that we have available to us. It is a finite resource, and it's very important to all of us. Okay, so let's look at the watershed. And what is a watershed? It is basically the area where a drop of water will drain to a major river system. And in our case, our watershed is the Umatilla River Basin. So this is the outline of the highest area along the basin, and all the water that falls in this river basin will migrate towards the Umatilla River and out to the Columbia River. The Umatilla River is a sub-watershed of the Columbia River Basin. So the Umatilla River also has a multitude of sub-watersheds, for example, from Meacham Creek, Mackay Creek, Buttercreek, and Wild Horse Creek, the like. So now in our watershed, we have the Blue Mountains to the southeast and the Columbia River to the north, and the Umatilla Reservation in the foothills and mountainous areas of the Blue Mountains. All right, most of the water falls in the Blue Mountains. We have as much as 50 inches of rain and snow. We call that precipitation. And it's semi-arid to arid in the lower Umatilla Basin with 7 inches of rain and snow. And for practical purposes, very little of that water actually reaches the groundwater system. So it's believed most of the recharge that happens to the groundwaters is in the upper basin where most of the rain falls. Okay, so let's look at the water cycle. This is a complex diagram that shows many aspects to the water cycle and the free flow of water to in many directions. But let's look at the 3 basic elements in these big lines here. This is the evaporation that occurs from surface waters to the atmosphere, and we have then condensation to precipitation as snow and rain, and then we have runoff down along the surface in the watershed, as we spoke, and also groundwater runoff in the subsurface in the watershed. So each of these is a discipline unto itself in which to study, but those are the 3 major categories in our water cycle. The water budget in our upper Umatilla River Basin is basically something that we outlined here in diagrams of where water flows. So we have the evapotranspiration, which is evaporation and transpiration from plants combined into one word, precipitation, and then we have the runoff along the river. We have springs discharging in the foothills mountainous areas, and we have groundwater development from domestic wells, municipal wells, and agricultural wells. This picture also illustrates that we have recharge to the shallow and deeper basalt aquifers, and we'll look at the flow paths of groundwater in another slide. But notice that there's soil moisture along a thin veneer here too. So this is what people have done to monkey with the water cycle, and they've redirected water, dammed it up, leveed, and the like, and have really altered the course of water. But we see we have the evaporation, the evapotranspiration, cloud formation, but we've also attempted to, seed clouds and try to produce more rain, more precipitation. We have runoff, we have irrigation now development, and diverting of water to fields, water for livestock, and water for cities. So I jokingly say that now water flows to money. So what is groundwater? That's one of the first things that we need to understand, is that groundwater is not underground rivers like we see on the surface. Groundwater is really water that occupies the pore space between these rock grains. Okay, so this is saturated material with water, and above the water table, it's unsaturated soil and grains and air and water. So we have what soil moisture in the what we call the Veda zone above the water table with air and water, and then below the water table, everything is saturated, 100% saturated with water in the rock formation. Imagine a jar of rocks, dry rocks, and then take about a third of that space, and then you could pour water into that jar of rocks to occupy the pore space. And that's how much water is in rock formations. We really have a lot of water and storage capability in the subsurface. And that's why we have 30% of all our fresh water is in groundwater. There's a lot of storage down there. Okay. So this is an example of the water table, and you've heard that probably many times. Okay, so for the most part, groundwater is invisible. We really don't see it in the subsurface. But we do see it in springs and seeps in the hillsides. This is Homley Springs on North Reservation. And these clumps of trees are springs as well. And they're self-feeding kind of vegetation growth and development, with water providing source for tree development. And then there's organic matter that then provides support for soil structure and development. And it's a feeding cycle into itself. So we have more trees with the water. And you can see this is a cluster of trees in a line, and that might be from the groundwater discharge area along an interflow zone. And sorry, I didn't mention the interflow zones in the previous slide where we get our water. We'll see it in another picture, however. Okay, we also see it in cisterns and boreholes. This is a moonshine cistern where we have a spring bubbling up here that was developed, and then if the valve was closed, it would fill this cistern. This is looking down a well, and that's the water table. That's the everything below the water table is saturated ground, and above it is unsaturated with the air and water for soil moisture. So that's a cool picture of what it looks like in the borehole. And we see groundwater in rivers and creeks, and it's like, well, wait a minute, this is surface flow, right? This is what we just talked about, that 1% of 3%. Surface water is mostly supported by base flow, which is groundwater discharge. So that base flow is something that's a kind of a new concept for many people. Okay, so let's look at what base flow is, and we'll see that an interconnection of groundwater, surface water. So here's a picture illustration of the Umatilla River in Pendleton. We're looking at the 8th Street Bridge here, and this is the river levee and the Blue Mountains in the background. And in the subsurface, we have the basalt flows that we see in the landscape, right? And the stage of the river, the height of the river, and then this is the water table and the alluvial depositional material that would constitute the floodplain that we mentioned in the river vision, the connectivity of the river to the floodplain. And as this illustration shows, there is a disconnect of the Umatilla River and high waters flowing out into the floodplain because the levee prevents it. So it's contrary to the river vision and a fully functioning river system. So beneath the river and in this, we have those basalt flows. And between each basalt flow is an interflow zone along here. And if it's, if it stores water and transmits water, then we call it an aquifer. All right, not all groundwater are aquifers, but if there's, again, sufficient flow and storage in a rock formation, it's called an aquifer. All right, so this is how groundwater, surface water is connected, and this is how the river is supported by base flow or groundwater discharge. This image shows the water table sloping away from the river, so this is a losing reach of river. And if the water table was, for instance, higher than the river, then it would be a gaining reach. So let's see now how we measure how much base flow is in the river. And this is a picture of a gauging station in Gibbon, Eastern Reservation boundary, and Umatilla River. And it measures the height of the river, and we relate that height to a specific discharge. And so with different heights, we have different discharges. And the gauging station, this is a hydrograph of the average flow for the period of record, 82 years of record. So these are daily average flows and shows you where most likely going to have high flows and low flows. Whoops, sorry. So these are the flow rates in cubic feet per second. And this is the calendar or the water year beginning October 1st and ending September 30th. And these are the high flow periods, and this is the low flow period. Throughout this entire period of record, you know, groundwater and surface water are connected, right? So there's base flow throughout the year. This red line shows the average monthly flow, and through analysis of the hydrograph and the record, we can determine how much of this is base flow and how much of this is surface runoff. Okay, so this is the average monthly flow at the Gibbon station, and the average annual is 230 cubic feet per second. And through that analysis, we determined that 20% of the annual flow is actual surface runoff and 80% is base flow from groundwater. Most of that base flow is coming from a very local flow system. All water needs to do is seep into the ground through the soil to a water table, and it then discharges to the river. So the floodplain is integral to this support of base flow in the river system. And groundwaters not only provide the water quantity, the supply in water, but it also moderates the stream temperature of a stream. Have you ever noticed jumping into a pool in the river and all of a sudden it's cold at depth? And well, that's groundwater discharge to the river system, and it helps moderate the stream temperature. So this is the Umatilla Basin watershed that I had pointed out, and underneath the entire watershed is that Columbia River basalt system. And we get our drinking water mostly from the basalts, though there are some people who draw from the sedimentary deposits. So the next slide is going to be a cross-section across this river basin. And we'll look at how we share the entire groundwater system. All right, so here's that cross-section from the Columbia River to the Blue Mountains, and the Umatilla Indian Reservation is out here. And this is vertical exaggeration, a considerable amount, but to be able to see these wells in relation to each other. This is the Hermiston area in Stanfield, and these are typical irrigation well depths. And here's the city of Pendleton, typical irrigation well depth, and the tribes have several deep wells as well, which is, this is an irrigation depth for well 4. So you see that we all share this basalt formation, and we share the aquifers in the Umatilla River Basin. These are the basalt aquifers. And we have a considerable amount of irrigation development in the lower basin and relatively little irrigation in the upper basin. We have mostly dryland wheat. This is important because areas where we have high development, high capacity wells, we have groundwater overdraft, meaning we're mining the groundwater. Since wells have gone in, water withdrawn in a high producing way, water levels have declined. And over the 70 years, it's declined as much as 500 feet. We'll look at some hydrographs of that in the future. And these, in 2012, some recent studies have identified that the water level declines observed in the lower Umatilla Basin are also observed in Pendleton, and they share the same hydrologic system, and that's been shown. And Pendleton's observed about 100 feet of decline, and like again 450 in the lower basin. These faults here have broken up the continuity of the groundwater flow system, and we do not see water level declines on the reservation, and this could be because of a couple of things. One, the faults and compartmentalization, and we don't have high development on the reservation. So we are, and we'll see those hydrographs. So these water level declines prompted Oregon Water Resources Department to implement critical groundwater areas, and the next map is going to show those areas. We have the Stage Gulch critical groundwater area, Buttercreek, Ordnance Gravel, and Ella Butte. And Pendleton is not in a critical groundwater area, though I said they share the same aquifer. This, things are evolving and our understanding of the flow system is developing. But Pendleton has worked to counter the groundwater level declines with aquifer storage and recovery. Okay, so let's look at the, here, we're going to look at water level declines in the Buttercreek area, in Pendleton, and on the reservation in Mission. This is a hydrograph of the groundwater levels in the Buttercreek area. And this well, when it was drilled in 1953, it was near ground surface. It was almost a flowing artesian well. And over the years, with development and mutual development, neighboring wells, the water levels have declined. And this is as much as 450 feet over those years. And with the implementation of the critical groundwater management areas and cutting back irrigation use, the water levels are starting to stabilize, though they have not. This is the city of Pendleton well, and this has had almost 100 feet of decline, and with the aquifer storage and recovery, we're getting a slower rate of decline and hopefully in the future some stability. This is a reservation monitoring well. There's no development on this well, though we see on these monthly readings that there is seasonal effects on the groundwater levels. And every year, however, the water levels recover. So there is not, if we were to just plot the spring highs, like these are spring highs, we would see a very straight line. But with development, we have mutual interference and we have water level variability through the season. The tribe's water code implemented restrictions on groundwater development in the Mission Basin in this area and have limited use to 25 gallons a minute, and that has arrested these seasonal, this extreme seasonal variability, and now we have little well interference. Okay, so let's see what we've done to the water cycle and to our watershed. And this is a complicated slide, but what's important is that it shows areas, the white arrows and the red arrows shows areas where people have affected the water cycle. White arrows are natural processes taking place, and the red arrows is people affecting process. And the black lines is the basic big regional flow system directions. Okay, so in the Umatilla, like this picture shows, we have a big regional system like would occur in the deep basalts. And then we have an intermediate system like the foothills to Pendleton or to the other areas. And then we have a local flow system, like from what would occur in the floodplains and along the river. And in this, we have roads, we have wells, we have septic systems, we have farming operations, we have mining operations, and all of these areas are places where we can pollute our water resources. We can add nitrates, like in the lower Umatilla Basin, overlapping all that critical groundwater area. Well, most of the lower area is a groundwater management area declared by the Department of Environmental Quality, and it has high nitrate contamination. It's been going on for 30 years plus. It's difficult to treat groundwater once it's contaminated. Fortunately, we are not experiencing that in the upper basin. But we do, on the landscape, affect our water cycle, as I showed in the cartoon previously, that we redirect water, we pollute water, and now, this was a 1980s poster, and this was before, there's widespread acceptance of global warming. Now people are, people are affecting the atmosphere and the global cycle, the global water cycle, and we are heating up the planet, and that causes more evaporation, more water is a greenhouse gas, more water in the atmosphere, which is then changing our weather patterns and our precipitation character from in the Pacific Northwest, from snow to rain. And so this is a major global aspect of our water interference, you might say. All right, so with global warming, we have some predicted future conditions for the Pacific Northwest. Scott O'Daniel will be talking about future flows in the Umatilla River Basin, and I extracted these bullet points from Kyle Dittmer when he did a 2015 presentation for the tribes. In his presentation, he discussed these points. An increase in average annual temperature ranging from 3 to 10 degrees Fahrenheit by the year 2100. The annual precipitation is projected to either decrease or increase from negative 10% to positive 18%. So we'll have, throughout the region, we'll have positive and negative total precipitation. There is virtual certainty that extreme cold days and nights will be warmer and occur less often. There's virtual certainty that extreme hot days and nights will be warmer and occur more often. And it's very likely that frequency and duration of heat waves will increase. And this is related to the heat waves in the summer within a year. And it's very likely that heavy precipitation events, the frequency, intensity, and/or amount will increase in our region. Well, this was a 2015 slide, and while last year we had a flood of record where we had quite an intense, we had considerable snow and then warm Pineapple Express atmospheric river come in and melt all the snow in the lower parts of the basin and just provide us a deluge of water for a flood of record. And it's likely that drought will increase in duration and/or intensity. And it's likely that low-level mountain snow will decrease by 40% for April 2040. Now, low-level mountain snow, that's significant. We rely on that snow for groundwater recharge, the slow melt and the slow infiltration of groundwater. Okay, here's just a break between slides of text, and this is the Blue Mountains with snow in the hills, and this photo is from Eric Klemps. So the implication of global heating, climate change on the first foods. With warmer annual temperatures, we anticipate changing weather patterns, changes in snow distribution, and a period of snow melt. So less snow and early onset of snow melt will lead to less time for melt to seep into the ground as soil moisture and as groundwater recharge, as I mentioned earlier. Less groundwater recharge means there's less groundwater discharge to streams and springs. Remember we talked about the base flow component? Less groundwater discharge to springs means there's less water for trees in that image of the Blue Mountains with a spring and a seep. Less groundwater discharge to streams results in less in-stream flow and less moderation of stream temperature, so temperatures in streams will rise. And with higher temperatures, there's more algae growth, there's less oxygen, less biotic diversity, poor aquatic habitat conditions for first foods. Here's another break. This is salmon spawning, adult salmon spawning. So this is continuation. So less spring runoff and warmer waters will have impacts to the life cycle of salmonids, from spawning, incubation of reds, emergence, rearing, outmigration, and adult returns. We'll probably have a presentation on the effects on salmon in the future. So less water and warmer water in stream will result in less first foods. And so, you know, as well as the impacts to the first foods, will also have more and greater intense floods, more and longer droughts. It will be harder to predict the water supply, and water management will be more difficult due to the extreme weather conditions. How do we plan for, you know, crop growth and water releases and the diversions that we employ on water? And in addition, with that early onset of snow melt, we'll also have, and warmer temperatures, will have a longer growing season. So that means there's more demand on shrinking water supply, which also pits irrigation water against in-stream flows. So this is a picture in February. There's no snow. Notice there's no snow. This is February 2020, overlooking Thorn Hollow and the Eastern Reservation. And this is after the storm had melted all the snow, and we had a record floods in the Umatilla River. And you can see the river from a great distance here. All right, so what can be done to adapt to the changes in climate? Well, we can implement river vision and first foods upland vision. That's an important aspect. If we're doing what it calls for, we will be protecting, enhancing the first foods and adapting for climate change. So we can promote natural storage in floodplains, less levees, groundwater recharge and development of ponds, more beaver action. We can reduce greenhouse gas emissions by using more green energy, such as solar and wind, and less fossil fuels. Ride your bike, walk to the store, do what you can. And we can plant more trees for carbon sequestration or storage of carbon. We can increase our climate stations. You saw in the pictures the mid-level elevations, but we don't have any monitoring sites in those mid-levels, so we don't know how much snow and how much rain falls in those areas and the changes that might occur with climate change. And most of all, the things that we can do is we can conserve, we can employ conservation in all aspects of our daily life, reduce, reuse, recycle, repurpose, and reduce those greenhouse gases. Okay, so sustainability of tribal people and culture is directly related to the success of first foods, right? Okay, and the corollary to that is what's good for tribal people is good for America. This came from an Anton Minthorn quote during Water Commission. And so it behooves us all to protect, restore, and enhance the first foods and to adapt for changing climate. Okay, that's all. Thank you.